Good morning and good evening, wherever you are. Today we're going to do 10.6. We're talking about tangents. I didn't write that on here, that's what I was going to say. We're going to be talking about tangents. That is not how it's supposed to look. Tangents and their relationships, okay? So tangent, obviously our first object, like as always, is going to be the word we're talking about, tangent. That's a G, okay? A tangent, to me, if you guys have ever been in like a conversation with somebody, you guys get lost, you guys get off track on a tangent, right? Like if you're talking, and like, let's see, how can I draw this? This is me talking. Here's me talking. All right. The conversation is like, kind of like this. Okay. And then you have like a side conversation that comes off on a tangent, and you guys are talking about something else. You know what I'm saying? Like these are different subjects, right? Like these things we're talking about, they're different subjects, but they were related at one point. Like they had one thing in common, and then we kind of got off track, right? So a tangent and a circle is the exact same thing. It's a line. I'm going to stress that it's a line that is related to the circle, that touches the circle, in only one place. In only one place. Okay, if I came over here and I draw that, I'm going to pick a point. Now I have to pick a line that touches that point I just drew at only that point. It touches touches the circle I just drew at only that point. How am I going to do that? I'm going to have to come over here, right? I'm going to draw like this. You guys probably think of this on your own, right? Here's a line. It touches that circle only at that point. It's tangential, is what you would call it. It's tangential. This line here is tangential to the image. Okay? So, what can I do about this? How can I write this in terms of mathematics? I want a line that intersects the circle. So it's really just that word change, intersects the circle at only one place. At only one place, okay? Later we'll talk about lines that touch in more than one place, but today we're only talking about tangents, right? So if you have like a line like this, that's not a tangent, right? It touches at two places, right? So let me ask you a question, guys. Can a chord be a tangent? No, for two reasons. First of all, it touches at two places. And secondly, it's not a line. It's a segment, right? It's not a line. Okay? What about this guy? And later we're going to talk about tangent segments, okay? So this segment is tangent, but the segment is only tangent if the line it makes is also tangent, okay? Does that make sense? Like I could draw, how did that happen? I can draw, maybe if I should get my eraser. I can draw a segment like this, okay? That only touches at one point to the circle, okay? But its line, if I continue it out, it touches in more than one place. It touches in two places, okay? So that would not be a tangent segment, all right? The line it makes has to touch in only one place, okay? And our next word for today is the point of tangency, and I'm sure you guys know what this means. So the point of tangency. This is the point where the tangent touches. This is the point where the tangent touches. Where the point where the tangent touches the circle, okay? Touches. All right? And to math, this point is just the intersection. The intersection of the tangent line, and a circle, and just to be clear, these are supposed to be G's, okay? Tangent is spelled like this, T-A-N-G-E-N-T, okay? Tangent. Just like a conversation, right? So here, if I drew another tangent line, like I kind of drew my previous guy, okay? This line, L, is tangent to the circle, okay? The point I'm talking about, of course, is this point. This is the point where that tangent touches. This is the intersection, right? This is the point of tangency. The point of tangency. Just that point is what we talk about, right? That's why it's, in the name is this point, right? Point of tangency. Okay. So, common tangents. This is a fun kind of puzzle idea. Okay, that isn't, you guys will need to know this to make some tangent conclusions, but it's not really like a theorem or anything. So I encourage you guys, I'm going to do two of them, and I encourage you guys to try the others, okay? I encourage you guys to try the others and come up with them on your own. It's more of a puzzle idea, okay? Well, actually, how about this? I'll go over all of them really briefly, but if you want to pause here and try and figure them out, you can. But maybe watch this first example to see kind of what I'm talking about. I want to find every single, I don't know why I'm drawing these lines yet. My goal is to find, if I can write this, find all the lines that are tangent to both circles, that are tangent to both circles. That are tangent to both circles, okay? That's what I want to do, just so they're super clear. Okay, so the first one I can do is this one I see. Oh, look, there's a line here, not there, right? There's a line here. If I make this straight, maybe it'll look better. A line right there, right? That touches this circle in only one spot in this circle. And it's not drawn very well, right? But you guys get the point. Touches the circle in only these two places, right? You guys see that? I don't know why it's acted straight now like that. Okay, there we go. It's not going to want to do it, of course. Okay. That line is tangent to both circles. So for this circle, there are only two tangents. There are only two common tangents for this pair of circles. Okay, if I move over to this next pair over here, how many do you guys think there is? Well, there's obviously two from this last image, right? Like from this, well, maybe not obviously, right? But these two images, from our last image, we can kind of see that we're going to get two again, right? We're going to get two tangents that they have in common. And then there's actually this third one hiding right here, right? If these circles are touching at only that point, then we can make that our point of tangency and be tangent to both circles. So there's actually three tangents. For this one, three tangents. Okay? And then for this one, what do you guys think? How can I make, for this one right here, this third one, how can I make a tangent to both of these circles? This one's confusing, right? Look, if I try to like, if I try to like do it like here, oh, I'm going to intersect the circle at two places if I drew this line. Okay? In fact, if I drew any line on this circle, I would be intersecting in two places, right? Like if I drew any line on this circle, do you guys see that? If I picked another tangent line to this circle, like right here, it wouldn't be intersecting in two places, right? Guys maybe see what I'm saying? It doesn't matter where you pick a tangent line to this circle, you're always going to end up that it intersects the other one twice. So this is zero tangents. There are no common tangents. Okay, there's no common tangents between these circles. Alright, now this guy is an interesting one. Okay, just like these previous, the first two we did, these guys are going to have two. These guys are going to have two along their like sides. I mean, like I say, like to us right now, it looks like they're top and bottom. Cannot draw a line today, right? Oh, it's so bad. Okay, so these guys looks like they're top and bottom, right? And then, like last time, these guys aren't touching at one point. Look at this. There's some more tangents hiding in here. If I draw this line through here, there's one, right? There's a line that touches both sides. And then also right here, there's a line that touches both sides. Okay, look at that. So here we see there are four tangents. Four tangents between those guys, okay? I want you guys to, on your own, try and draw a picture. Try and draw a pair of circles that has only one tangent, okay? It is possible. It is possible. Try and draw circles that have only one tangent line in common, okay? So for this one, this theorem is our first theorem. You guys, of course, try it on your own. I'm going to go over it real fast. This theorem is named after whoever discovers it. What do you notice about the angle created by the tangent line and the radius? What do you notice about these angles? Well, just from looking at it, it kind of looks like 90, right? But, we're not allowed to, like, mathematically assume that, but we can kind of see it looks like 90. So, the idea here is to think about this. The idea here is to think about this in terms of what this tangent means, okay? In terms of what this tangent means. And this isn't a very rigorous proof. But I'm thinking in terms of, like, let's assume it's not 90. Right? Like, if we assume this angle is not 90, then, this guy still adds to 180, right? So this guy still adds to 180 regardless of if it's 90 or not. But let's assume this angle here, like, just for the first part. We'll assume this angle here is, like, 80, okay? Or no, let's get even closer. We'll assume this one is, like, 91. And we'll assume this one's like 89 degrees, okay? So they're not quite right angles. If they were like pretty close but not quite right. Well, what would happen? What would happen if that was true? Oh, well this guy's angle, this tangent line, it would have to be tilted just a little bit. Do you guys see that? It would have to be tilted just a little bit. Oh, and what happens when that tilts? If that tilts, then we're going to get that this guy intersects twice. So it's not a tangent. Okay, right? Now if I tilted it the other way, if I said, oh, okay, maybe this angle, maybe it's actually the other way. Maybe this guy's 89, and this guy's 91. Oh, look, I'm going to get the same thing, right? Look, this guy's going to have to be tilted just slightly, just 1 degree off, right? And it's going to have to touch the circle in another place. You guys see what I'm saying there? Okay, so that means, just to keep it, so if we're being very mathematically proper, just to keep it, that would be called a proof by contradiction. Okay, a proof by contradiction. This guy must be 90 degrees, okay? So, here we're going to write it over here. A tangent line is perpendicular to a radius of the circle. Tangent line is perpendicular to a radius of the circle. Do you guys see that? Here's a radius, and here's our tangent line that I've drawn. Okay, TL for tangent line. He's tangent, so he's 90 degrees. Okay, so what about this one? What about this one? Oh, and I should say the tangent line is perpendicular to a radius of the circle at its point of tangency. At its point of tangency, right? That's the point we're talking about. It goes to here. This P, this is the point of tangency. Okay, cool. So down here, same kind of deal. Look at this. I can make, first of all, I want to know what's true about these bolded segments. So I'm talking about these bold segments, okay? What I can do, first of all, is I can say, oh, look at this. I can make 2 radii that are the same length, okay? And look at this. I know they're 90 degrees by the previous theorem I just made. Here's a radii that touches the point of tangency. This is a radii that touches the point of tangency, so it must be 90 degrees. So what I can say here, what I can argue here, something cool like this, right? Maybe I'll make a straight line. And I'm sorry if you guys can hear the music outside. I don't know what they're doing. So check this out. Here's what I'm going to look at. I'm going to see these lines are the same. It's like these triangles, these 2 right triangles share that side in common. Oh, look at this. Here is a right triangle. Here is a right triangle. Right? These guys must be congruent by HL. So they're congruent by HL. Congruent by HL. And you guys don't need to know this, but we're writing it out so we can see the point. So what does that mean? That means these segments must be equal. These segments must be equal by congruent parts of congruent triangles are congruent, right? Do you guys see this? Okay, so check this out. Check this out. All we need, here's the cool part for this, and I'll erase this. You guys can leave it on your paper. I'm just gonna show you guys what I mean right here. All you need to get these segments are congruent. This is very powerful. People use this in math all the time. All you need is 2 tangent lines that touch at a point. That's it, guys. All you need are 2 tangent lines that touch at a point. Tangent FE and tangent GE. They intersect at a point outside the circle, so it has to be outside the circle. So here's what you can write. Tangents that intersect outside the circle, form congruent segments. From F, excuse me, in this case it's from F to E, but maybe we'll write it like that. From F to E, and from G, well, actually, let's write it like this. They form congruent segments FE, okay, FE, and GE, okay, where E is their intersection. So look, what I didn't want to write right there because it would be too long, I think, for you guys' tiny paper, is that you want to go from your point of tangencies to a point outside the circle. So as long as you're doing that, this theorem is true every time. This theorem is true every time because you can always draw these triangles, right? That's kind of why you can always draw those triangles and make that argument. Okay, cool. That's it for that guy. Last thing for today, we're just going to do a couple examples. So, apply what you know to solve the following values. Assume the tangency for segments, which appear tangent. Okay, so this guy looks tangent, so that the instructions are telling us that he must be tangent. Okay, so we're assuming he's tangent. Now, if we look here at 2x plus 4, this is describing the length of this segment. This guy's describing the length of this segment. Well, we just found out from our previous theorem that, look at this, these 2 lines are tangent, right? These 2 lines are tangent to the circle, and they intersect at this point. Okay, well then these segments from the point of tangency to the point of intersection must be congruent. Okay, so since these are congruent, I'm going to set them equal to each other. 2x plus 4 is equal to x minus 4. Okay, and if we add 4 to both sides, we'll get 8 on this side is equal to, and we'll subtract, of course, I've set this up wrong, I think. Okay, let's see. I guess this is supposed to say 3x again. Have I done this again? Let's see. 2x plus 4 is equal to 3x minus 4. Look, you guys learning with me. All right? So, yes, now we will get that 8 is equal to x, which was the intention. So, I'm sorry. Change this on your thing. Change this to 3x, and I'll make this in orange so we can see. Change this to 3x on your paper. Okay? My bad, guys. My bad. Didn't check my exercises enough. Got to check them again. Okay? So, and this was one of the first ones I made, so that makes sense. Okay, so, looking at this guy, what do we see? What do we see here? So there's two ways to go about this. Well, actually, no. There's only one way that we're going to show. There's only one way we're going to show to go about this. So I see that this segment is tangent because the direction said so, right? So this segment is tangent right here. I mean, excuse me, the line is tangent, so the segment is tangent, okay? Which means this segment is at a 90-degree angle to this one. Do you guys see that? Because it's, the radius. This is the center right here. I haven't marked that either. So this is the center right here, right? What can I do to solve this? Oh, I hear you saying Pythagorean theorem, right? Now we're like an episode of Dora. So b squared plus 12 squared is equal to 12 squared. How is this 12? That can't be 12. That's not how this works. Oh, excuse me. I misread it. Ha ha ha. Going back. Just kidding, guys. Here's what we're going to see. If this guy is 12, then this guy must be 12, right? You guys see that? That guy must also be 12. Oh, cool. Okay, so what's the length of this whole side? The length of this whole side is 16. I tricked myself. Haven't looked at it so long, I tricked myself. Okay, so here's what we're going to see. So see how I caught my error, though? I saw that, wait, you can't have that the leg is longer than the hypotenuse, right? I looked over here, and I said, oh, the leg can't be longer than the hypotenuse, so there's a learning opportunity for you guys, right? That's how I checked my work and saw that I was doing something wrong, okay? So check this out. I'm going to get b squared by Pythagorean theorem. Let's write it this way, like we did in class. C squared is equal to a squared plus b squared. This is all the way from unit 9, okay? And then we're going to get, let's see, 12 squared equals, excuse me, I did not mean to write that. I meant to write 16 squared there. 16 squared, too tired today, recording this too late at night. All right, let's see. 16 squared is equal to, and then we'll get 12 squared plus b squared. Okay, now what I'm going to do is I'm just going to square these guys out. So I'm pretty sure I know the square of 16, but I'm not going to say it and make another stupid mistake. Okay, 256, I was right. So 256 is equal to 144. That's just me plugging it in the calculator, right? Plug it in the calculator, make sure I'm right. Okay, now I'm going to subtract 144 from both sides. Okay, and that's going to give me 112 on this side. Excuse me. 112, which is equal to b squared. All right, so b must be equal to the square root of 112, right? Because I'm taking the square root of both sides to cancel that guy out. Okay? And so the square root of that, let's see, the square root of that guy is about, if it would let me activate my calculator, there it goes, is about 10.6. So this guy's about 10.6. Okay? About 10.6. So that kind of makes sense, right? Actually, he should be longer. So maybe we've done something else wrong. Let's see. Square this guy. No, this looks correct. I must have just drawn my figure wrong again. Okay, so you got to be careful about these assumptions you guys are making. Okay, so over here, and on the exams and things, the figures will be to scale. Okay, I promise. I'm gonna check and double check and make sure. So this one right here is 2x plus 3. That's what this guy's saying. Just this piece right here is x, and this guy is 6. So okay, first of all, these guys are all tangent to this circle. The triangle is tangent to the circle. The circle is actually inscribed inside the circles. I mean, inside the triangles, what we'd call that, right? So, what do we notice? Well, this is kind of tricky. This is trying to trick you a little bit. Look at this, guys. These segments are all tangent. Since they intersect at a point, these segments are equal. Oh, these guys intersect at a point. Oh, these segments are equal. These guys intersect at a point. Oh, these guys are equal, right? Just by our theorem we did, okay? Okay, so here's what we're going to see. We're going to see what? If this side is 6, then this side is 6, right? Okay, so if I'm just trying to find x, all I need to do is find the length of this piece. Okay, so what I can say is I can say, well, I need that, if I write it like this, right, the length of this piece is the whole thing minus this tiny part, so I'm going to write this as 2x plus 3, I'm sorry. That's this piece, okay, minus 6, right, minus 6 to get this length. Okay, So here's what I'm going to set up. 2x minus 6, excuse me. Trying to work too fast in my head. 2x plus 3 minus 6 equals x, right? That's just by these segment relationships that I drew on. All right. So then I'm going to see, I'm going to, subtract 6, right? So I'm going to get negative 3 is equal to x. All right, then I'll get 2x is equal to x plus 3. And finally, I'll get that x is equal to 3. Okay, so this length is 3. That means this piece is also, maybe I'll do this in orange instead so we can kind of see what's going on better. This guy is 3, right? This guy is also 3, because they're congruent. Okay, this guy is also 6. Okay, so this whole side over here is 9 over here, right? That whole thing. Okay, and then if we use some clever tricks, we can actually figure out this side, but I'll leave you guys to see if you can do that on your own. Okay, so that's it for today. All right, you guys work on your assignments together, try and figure some stuff out. Okay, email me, Mr. Smith, the questions, ask in class. All right.